Welcome and thank you for attending this talk. My name is Frédéric Roucoulès. I'm a PhD student in France at CEA-List, Université Paris-Saclay and Université Grenoble-Alpes. I'm very proud and honored to present you today our latest result about how to safely deal with GNU-style inline assembly in C code. So, first and foremost, what is the inline assembly? Inline assembly is a special feature provided by some compilers like GCC or Ceylon, which allow us to directly embed assembly instructions inside the C sources, together with the necessary glue between C and assembly. We will see that soon. It is actually pretty common to use it in software development, either to have access to the hardware or to manually optimize the code. For instance, we found that more than 10% of the packages written in C of the Debian distribution contain some inline assembly chunks. Another study by Rieger and al. Reports that more than 1/4 of the top-rated GitHub projects make some use of inline assembly. Yet, the problem is, it is well known that writing inline assembly is really error-prone. First of all, let's see precisely what inline assembly is. An inline assembly statement is composed of a template, the actual instructions, which may contain some tokens to be substituted by the compiler, and what we call the interface that both describes how the instructions interact with the C context and how the compiler should instantiate the assembly. Actually, this code was working fine until a newer version of GCC was released. You have to know that compilers only look at the interface declarations. So, if the interface is incomplete or incorrect, like it is the case on here, the resulting program behaviors only depend on the compiler's current mode. And this is not an isolated case. We actually found several evidences of bugs related to code interface mismatch. So, today's challenge is interface compliance. As a first step, we need to define interface compliance, and it's challenging because the mechanism behind inline assembly are somehow unclear. After that, we want to find a way to automatically check that an inline assembly chunk indeed complies to its interface, and otherwise, we want to be able to patch it to make it so. And of course, we want to train it to be widely applicable, such that it should not be tied to a particular compiler or architecture. At the end, we claim the following contributions. We propose a novel semantics and comprehensive formalization of the problem of interface compliance, such that it's amenable to formal verification. We provide a method based on data flow analysis to automatically check the interface compliance, and furthermore, patch the non-compliant chunks. This method is implemented in our prototype named RUSTINA. We tested RUSTINA on all x86 chunks found in Debian JC, and we found a lot of issues. All of this can actually be replicated with the artifact provided with the publication. Finally, in order to assess how dangerous compliance issues are, we carried out a qualitative study and found that most of the issues can actually lead to bugs with today's compilers. That motivated us to start submitting some patches to projects heavily relying on inline assembly, and 7 of them have already accepted the applied the fixes. Now, let's jump into the details. As I said, defining compliance is not easy. There is actually no standard, and the documentation barely shows some examples of what is working. So, a lot of things should be reverse engineered from GCC implementation. But we did it in order to obtain a clear formalization of the semantics of, on one side, the assembly instructions which may contain some tokens, and on the other side, the interface with high-level C binding information and low-level assembly binding information. Thanks to this formalism, we identify two general conditions that are required to ensure the correct compilation of the assembly chunk. The first one, the framing condition, is split into frame read and frame write. We think intuitively to this condition as a read and write permission of the assembly. The second one is more subtle, and we call it the unicity condition. The unicity condition states that the result should be the same independently from the particular token assignment chosen by the compiler. Moreover, we can now express this condition in our formalism and then automatically reason on them. Now, turning back to compliance checking, you can see here the workflow of our prototype RUSTINA. RUSTINA is built on top of the pharmacy framework for C parsing and the BeanSec platform for semantic extraction from raw assembly. We then developed dedicated analysis based on data flow analysis to collect useful information about the assembly and somehow infer over approximation of the required interface. At the end, we compare what we have just inferred with the actual interface and take the appropriate decision, including proposing a patch. This is a rough overview of our technique. More detail can be found in the paper, like how we deal with token identification. Let's now jump into the experimental results. In this talk, I will focus on 3 research questions. On does RUSTINA perform? Are the compliance issues really dangerous? And what is the concrete contribution of all of this? The answer of the first question is pretty well. With an average time of 40 milliseconds per chunk, RUSTINA detects a lot of issues for both the framing and the unicity condition, and RUSTINA is then able to patch all but one subcategory of issues. So, if we look at the chunk level statistic, while only half of the chunk were initially fully compliant, 97% of the chunk are then fully compliant after our fixes. But okay, we found more than 2,000 issues in a lot of projects, but hey, they don't really break all day. So, is compliance issue really an issue? And if yes, why does it manifest only rarely? To find out for sure, we started to review and play with the non-compliant chunks. We identified C patterns or bad coding habits responsible for almost all the issues. Then we found out that each of these patterns is somehow protected by what we call an implicit protection. Take a look at P2 for instance. Prior to GCC 5.0, the compiler was prevented to allocate register EBX to the assembly chunk. Hence, a lot of code actually used EBX without declaring it. And when GCC changed its policy, the non-compliant chunks started to crash. That's for the why we don't see them. Now, about their severity. In addition to the already known bugs, we have also been able to break experimentally 5 of the 6 patterns by playing with compiler options and settings. So, the compliance issues are no future proof. They can break, and when they do, they are very hard to identify. To end this presentation, I just want to say a final word about the patches we already submitted to the developers. So, we already submitted patches to 8 projects covering more than 50% of the dangerous issues reported by RUSTINA. In conclusion, we can say the interface compliance matters. It is tricky to ensure, but it should not be a problem anymore thanks to RUSTINA. This talk is a quick overview of our work, so do not hesitate to have a look at the paper. Thank you for your attention, and feel free to ask any question.
Hello again. The second paper in this session is named Interface Compliance of Inline Assembly. Automatically check, patch, and refine. One of the authors is Frédéric Recullet, and he's here to answer any question you would like to ask. So please use the chat you have on the right on the screen and write any question you would like to ask. In the meantime, I'm going to ask him some questions. The first one is, how do you report the results of optimization or RUSTINA? Are they directly applied in the code, or do they require some decision from the developer? I mean, are they just displayed textually and the developer must to apply some changes on the code?
Yes. So in fact, for the optimization, we do not apply directly the change in the code because we think that some of them are not necessarily needed. So we just report it in the log with the reported issue. For the patch, for the safety patch, however, we directly apply the patch on the diff of the diff format to.
Okay, and it could be possible and a more automatization of the process. I mean, is it possible that as future work you could automatize the process and reduce the decisions that the analyst or the developer has to decide, or it's not possible?
For now, it's not possible, but in the future, we can think about uh, some some standard decision about some likely applied optimization and some others that are very unlikely to be applied by the developer.
Okay. Another question is about a subjective question. It's not a very technical question, but a subjective one. It's about the percentage of code that your approach is covering, because there are studies that state that there is a high percentage of code that is never used. So it's written, but it's poorly used. So, do you think that maybe this poor use of code could affect the results when you apply Rustina? I mean, this poor use of code involve a good value for Rustina because it is never used?
Oh, okay. Yes. In fact, I think that some of the chunk we are reporting can be never called. So in fact, there are just dead code inside the binary. But every chunk we use in your study were found in the binary form of the project. So in fact, they are on the binary executable. So maybe they are never called, but they are present. It's not just a part of the source code that is not only not called, but also not only compiled inside the binary.
Okay. My next question is about methodology. Your approach could be suitable for Agile's methodologies like Scrum or something like that, or it is more suitable for more traditional methodologies like a cascade methodology or RUP or something like that, or it's the same. It could be applied indistinctly to Agile methodologies or more traditional ones.
I think the execution time of our analysis and patch are very small, so it can be applied in both methodology. In fact, I don't think that assembly chunk, assembly code are really the core development during the. I don't think that assembly chunk are the target of change during of frequent change. So I think it can be applied once for the project, and yes, assembly chunks are very unlikely to change during the development project. So I think we can apply RUSTINA once for all the development phase, but in fact, you can apply it at each commit. The process time is very small.
Okay, we have one question from Paul. He's asking if does RUSTINA detect inline assembler chunks that are defined in macros, or what part of chunk is in a macro?
No, so in fact, for now, we are not supporting macro extension. So we are only processing the chunk after the macro were expanded. So yes, in fact, if one macro were used at a different place, we are analyzing different assembly chunks. So you need to pre-process your source files before applying RUSTINA. Then it will require manual effort to revert the patch and apply it in the macro to apply the patch on the sources with macro.
Okay, thank you. My next question is about your future work. What do you plan to continue in this line of research?
Yes. So, in fact, we report a lot of issues. Some of them can be are very unlikely to produce bugs. So we would like to integrate our work inside some compilers to have two advantages. The first one is it will be directly applied. It could be directly applied during the compilation phase, so it can directly warn the user that the assembly chunk is not compliant. And the second advantage is we can use some compiler knowledge about what register it's already used, and so we can filter some warning that will not be so some issues that will not be possible on this instantiation and this compilation code. So for instance, we can report an issue about a chunk that can overwrite register EAX, but in fact, during this compilation process, the compiler already use EAX for one purpose, so the problem cannot occur for this case. So
okay.
This is one piece.
So thank you very much. We don't have time for more questions. Very interesting work. So just receive a virtual clap from all the attendees that we are here listening you. And if there is any attendee that would like to talk with Frederick directly, you can go to the discussion room and he will be there to talk with you. Okay? So I hope to see all of you in the next paper. So thanks, Frederick. See you.
Thank you.